Okay, we'll get started here. Today I'm going to welcome Eelco Doornbos from the University of Delft. Eelco graduated at the Faculty of Aerospace Engineering at Delft University of Technology in the Netherlands. Early in his scientific career at TU Delft, he worked on data calibration and precise orbit determination of satellites measuring sea surface topography, with a special interest in improving the modelling of drag and solar radiation pressure accelerations. He subsequently worked on several contracts for ESA's Space Debris Office and Swarm mission, which led on to his PhD thesis in 2011. And since then, Eelco has worked on thermosphere data of, I don't know if it's GOCE or GOCE. Okay.
But there's a lot of confusion.
And on the more general topic of retrieving space weather-related data from non-dedicated satellites and instruments. He's currently assistant professor at TU Delft, combining his data processing and research projects with supervising several master's and PhD students and teaching courses on astrodynamics. And today he's going to tell us about thermosphere density, wind, and other geospace data from non-dedicated satellites and instruments. Thank you.
Okay, thank you for this introduction, and thank you all for being here, and for giving me this opportunity to talk about my work. So the title is maybe a bit strange, non-dedicated satellites and instruments. So let me just start by explaining a little bit about why I choose this title and not accelerometer satellites. I want to make this a little bit broader. So many satellites and instrument manufacturers have worked on space weather mitigation built into their missions and instruments. They might not even know that they should call it that, but so I think the most common example is dual frequency radio links, for example, in good quality GPS receivers, but also a K-band radio link in the GRACE gravity mission is a good example of that for mitigating ionospheric path delay if you want to make very precise measurements with radio links of distances. Accelerometers are also an example of the same principle. Basically, accelerometers were flown in the 70s and early 80s, I think, for aeronomy. But the golden age of accelerometry started not from the aeronomy point of view, but from the gravity field determination point of view. CHAMP is, of course, both aeronomy and gravity satellite. But actually the accelerometer is part of the gravity package. It was a sort of technology demonstrator also for the GRACE mission. Fundamental physics experiments now also start to carry accelerometers. And a third example is magnetometers that are on many satellites for altitude determination and control subsystems, but also for physics experiments. And of course, a satellite could also take a model of the geomagnetic field with it and a GPS receiver, and with the location you have the magnetic field. But you want a little bit more robustness if you're designing a satellite, so it's better to measure in situ the magnetic field. So this is another example of basically space weather mitigation built into satellites. So in this talk I'm going to spend, I think, 95% of my time talking about accelerometers and the thermosphere. But I think it's nice to keep in mind that this is a more wide overarching principle that is happening here. So first let me introduce the satellites. I think many people are already familiar with CHAMP. It was launched in 2000 and it decayed in 2010. It's not with us anymore. So this was this technology demonstrating satellite, aeronomy satellite, gravity field mission. The gravity field part was quickly superseded by GRACE, which was launched 2 years later. And the GOCE satellite, this European Space Agency satellite, is also a gravity field measuring mission. Well, the first accelerometers in the modern era that were really put on satellites to make thermosphere measurements were put on Swarm. Unfortunately, these accelerometers are not of the same quality as the ones on the other satellites, it turned out. But we have also the GRACE follow-on satellite coming up, and the microscope satellite currently in orbit. This is a fundamental physics mission. We're now in talks, well, actually, I think today my colleagues in France were in talks about a sort of extended mission and looking at using the accelerometers on this satellite to also make thermosphere measurements. This is a very interesting satellite. Actually, it carries 4 accelerometers. One of them contains proof masses of different materials, and the goal of the whole mission is to prove that Galileo was right, that basically, independent of the material, there's an equivalence principle in fundamental physics. I'm not a physicist, but basically independently of the material, the acceleration due to gravity must be the same. And then there's a whole second accelerometer with proof masses of the same material just to remove random error. Even one of these accelerometers would be enough for our purposes, but it's very nice that they make such nice instruments and put them on satellites. This is in a very high orbit, much higher than the other satellites that I'm talking about today, 720 kilometers.
So there must be more to the scientific justification of this than proving Galileo right.
Well, I think that is basically the scientific justification. I've been at one of the meetings in preparation for this mission, and there were physicists giving talk there. Most of it went beyond me. But yeah, there are a range of consequences that if you disprove that Galileo was right at a certain level of precision, then yeah, you can make interesting other theories. And one of these other theories has to do with dark matter, what they call a chameleon effect. And so it's not just proving that Galileo was right or was wrong. Of course, they are more interested in proving him wrong than proving him right. But I have not seen actually the publications yet from this. But it would be interesting. So, but back to the thermosphere, because I think that's what most people here are interested in, the thermosphere, ionosphere. So CHAMP, GOCE, GOCE follow-on, and microscope did not or do not carry their accelerometers for the purpose of thermosphere monitoring, but yet their data is very useful for this purpose. It has been used for improving empirical thermosphere models, expanding the database on which these models are built, validating and benchmarking empirical models and general circulation models, event studies, for example, geomagnetic storms, looking at what's happening in multiple types of measurements, including thermosphere measurements made by accelerometers, confirmation by observation of phenomena predicted by theory and models. I think theory and modeling are very strong tools in this discipline, and there have been many phenomena that were first predicted and then later proven to exist in the observations. And in some cases, you might be ahead of the theory and the models, and you might observe new phenomena that were not predicted, such as Herman Leur's famous paper on the cusp density enhancement. So just an overview of what we're looking at here. In terms of these satellites, this is a slide. I think there are a few slides at the start that I also showed at the CEDAR meeting. For those who are already there, it's a bit of a repetition maybe. But you can see that there are many satellites now at various altitudes, at various times. And they are all basically providing the same type of data, not all with the same level of quality. GOCE is my favorite, and I will be using it for most of my examples. You can see that it was in a very low orbit compared to the others, and it was kept at this constant altitude. Let me see if I can find my mouse cursor here. So for most of the mission, it was kept at the constant altitude, and then towards the end of the mission, the operators dared to lower it even further. And you can see that there was substantial risk involved, that if they would lose control of the satellite and the propulsion that kept it at the altitude would malfunction, then they basically would lose the satellite in a couple of weeks. Well, that's what eventually happens, but in an expected way when the propellant for this ion propulsion engine ran out. It's also interesting to look at basically the mean solar activity over this period. You can see that we have 1.5 solar cycle. Swarm is just starting. It looks like this will be a very long duration mission. There are talks about extending it at first at least until 2023. So then it will be a 10-year mission, but the satellite's in very good health, and I think if we reach 2023, there might be enough propellant left to keep it up for, well, I guess 5 or 10 years more, depending on the level of solar activity. This slide also already shows you a bit why we are interested in this data, because you can see that, for example, for GOCE is a good example. There are varying levels of orbit decay. At low solar activity, the decay is very slow, and then when we get to high solar activity, you can see that it's really ramping up, and the satellite is decaying rapidly. So if you're writing a proposal, you should always put something in there about why it's important. And well, the thermosphere is of course important if you want to predict satellite orbits, if you want to prevent collisions in orbit. You need to have a good understanding of the satellite aerodynamics, the forces on the satellite, and the density is really the major input, which has a lot of uncertainty at the moment. So this only shows the height. Of course, we can look at the orbital planes as well. That's also important, and there are important differences between the satellites. You can see that GOCE was in a sun-synchronous orbit, so it always flew more or less in the dusk-dawn plane. Towards the end of its life, it drifted a little bit away from this. There was no active maintenance of this orientation of the orbit plane. But you can see that CHAMP and GOCE, and the same is true for SWARM, they have precessing orbits. So they go through all local times, and you have to look, if you're looking at a certain event, or you want to collect a certain amount of data, you always have to be aware that it's going through different local times. The measurement principle of an accelerometer, it's actually very simple. It's actually a spacecraft within a spacecraft. So there's proof mass here. It's this metal block. And if you basically would not have any external forces on the spacecraft, you could basically imagine this floating inside of a cage freely. If it's undergoing the same gravitational accelerations, you put it in the center of mass, it's undergoing the same gravitational accelerations as the big spacecraft surrounding it, then they would basically move in sync. But now we have drag, basically air particles bumping into the satellite. Also radiation pressure has an effect. This basically pushes the satellite from the outside, but of course the block is shielded from that, so they will move relative to each other. This can be measured and compensated with electrodes, so you can put electrostatic forces on this block, and basically the voltages that you have to apply to these electrodes is proportional to the acceleration. And you can see that there are multiple electrodes in one plane here that is also designed to keep the rotations in check. GOCE actually had 6 of these accelerometers on arms. Basically the center of each of these arms was at the center of mass. So if you take the average of 2 accelerometers, then you get also a measure of the accelerations external to the spacecraft, the non-gravitational accelerations, the drag and the radiation pressure. They were put in this configuration because actually the scientists were more interested in the differences between these acceleration measurements, because they were basically outside of the center of mass. So gravity pulled differently on one with respect to the other, even though there was only 1 meter or less than 1 meter between them. So the differential acceleration was basically the main measurement for the gravity people, and this proved to be very successful. There's another important measurement principle that's often forgotten, but I think it's equally important. That's all of these satellites have very accurate GPS receivers. The problem with the accelerometers is that they are designed to be very stable within a certain measurement bandwidth, and for gravity, basically they're interested in very fine scale features of the Earth's gravity field. But the measurements basically drift away at longer time and spatial scales. And that is why we need to measure these accelerations at these longer scales in a different way, and the GPS is very useful for that. GPS is of course basically a range measurement, a sort of position measurement. If you combine multiple satellites, you can put all these measurements into an orbit determination where you have models for all the forces acting on the satellite. So what we do is we put the most advanced models for all the gravitational accelerations in our orbit determination, but we act as if we do not know how to model non-gravitational accelerations, and we put a sort of stochastic model in there where we estimate how large these non-gravitational accelerations are, and then we can compare these non-gravitational accelerations from the GPS with those from the accelerometer, and then we can combine them based on their frequency spectrum. So then we have a good measurement of the non-gravitational accelerations, both at long wavelengths and short wavelengths. But we're interested in the thermosphere, so we need to isolate aerodynamic accelerations. And so we need to look at what is actually measured. It's the sum of all the non-gravitational accelerations. That includes the aerodynamic acceleration, the solar radiation pressure acceleration, and on most satellites there's also some sort of thrusting going on. On GOCE it was this continuous ion thrust that was actually regulated by the accelerometer. So basically the length of this arrow is kept the same as the component in the satellite body fixed frame of the aerodynamic acceleration. So we're measuring basically the sum of all three. Then this means we need to model the other two that are shown in this picture. There are even more. There's also reflected radiation of the Earth. There might be micrometeoroid impacts. So some of them we cannot really model. They might show up as outliers in our data. But for most, we have some sort of model. We know where the sun is with respect to the satellite. We have some idea of what the reflectivity is of the satellite. So we can model all these other accelerations, remove them, and then we end up with the aerodynamic acceleration. Of course, any error we make in these models will show up in the end as an error in the thermosphere product. So that is important to keep in mind. Especially if you go to very high altitude, at low solar activity. For example, where the swarm satellites are now at 460 to 520 kilometers altitude. We're now approaching the solar minimum, and we're having a lot of trouble getting good data from the swarm measurements because basically the radiation pressure is about the same order of magnitude as the aerodynamic accelerations. So this will solve itself eventually when the satellites go down in altitude and when solar activity starts to rise in a couple of years. Yeah, this is important to keep in mind that at these very low levels of drag, you have large errors in your data. So now we have these aerodynamic accelerations. We want to convert them to density and wind. This is also a movie that I showed at CDAR. So we can have basically a sort of forward model. We know the relative velocity of the atmosphere with respect to the satellite. If you talk to aerodynamics people, they always want to basically picture themselves sitting on the satellite and looking at the velocity of the particles coming towards them. We might be more inclined to basically attach ourselves to the atmosphere and see the satellite going with high speed past us. But yeah, let's go from the aerodynamic point of view for now. So we have this relative velocity of the atmosphere, which points in this direction. This is, of course, the orbit velocity, plus the co-rotation of the atmosphere, if you think of the orbit as an inertial coordinate system. And then you can add, on top of the co-rotation, you can add winds. So I have not added any winds here, so this is just co-rotation for the simple model. And then we have a satellite aerodynamic model, which consists of a geometry model. We need to know the shape of the satellite, and we need to know how the particles interact with the satellite. That's also not so easy. I put it here in a few words, but that's basically an entire discipline as well, in which not much research has been going on, unfortunately. But if you combine all of this, you get some modeled acceleration out of it. So this is a sort of forward model. And then, of course, you can try to look at the real data. And this looks quite different from the modeled accelerations. There are some similarities, you can see. But this is a period of GOCE data where there was a magnetic storm going on. And you can see the measured accelerations acting quite nervously, quite large fluctuations. So what I do is basically, this is the algorithm that I developed for my PhD thesis. It was actually based on earlier work by Jean Bruinsma, but also Markels and Forbes from the 80s. What I do is sorry, I have to start the movie again. I basically assume that the difference in the direction between the observed and the modeled acceleration is due to the wind. So then I can add a wind factor, that's this green factor here, to the original relative velocity, which did not include winds relative to the co-rotating atmosphere, then you can see that there's a rotation going on of this relative velocity, the light blue arrow with respect to the darker blue arrow. And that causes a rotation basically of my modeled acceleration. And if they match, I have found the wind. So that's step one. And then step two is, depending on this direction of the relative velocity, I can evaluate my aerodynamic model. And you can see that there's also a difference in the length of the arrows then. And this difference in the length, I try to explain completely from a difference in the density between the reality and the model. This is not entirely correct because there might be an in-track wind component. But yeah, we have to do this way. And to do it in this way is actually, I think, the best possible solution, because this in-track wind component is maximum a few hundred meters per second, compared to the nearly 8 kilometers per second of the orbit velocity. You get a small error, but it's not possible to distinguish between in-track winds and densities. So we use a model. We basically use HWM model for the in-track winds to try to get rid of these errors as much as possible. But we know that HWM is far from perfect.
What is
HWM is the horizontal wind model. It's the empirical model that is currently being maintained by the Naval Research Lab. So Doc Drop and John Emmert. Yeah, so please interrupt me if there's anything unclear. Yes?
gravitational field from, say, solar lunar, is that normal?
So basically on the proof mass of the accelerometer and on the satellite itself, these gravitational accelerations, they act in the same way. So for the accelerometer, we don't have to worry about it. For the GPS, we have to put all of these accelerations that are gravitational in origin inside our orbit determination model when we estimate when we want to estimate the non-gravitational accelerations. So we even include Venus and Jupiter, and so I don't know. I guess that at least the sun and the moon are quite important, and they would lead to substantial error if we would not put them in the orbit determination. So I would like to give a few examples of what we can do with this data. And we actually did a project for ESA, for the Space Debris Office, on the GOCE reentry. They had tried to predict, when the fuel of GOCE ran out, how long it would take for GOCE to re-enter. And they basically were always quite off in this prediction. They basically thought that it would re-enter in 2 weeks, and in the end it was 3 weeks. So that was at the beginning, but also on the final day, they thought it would re-enter in 3 orbits from now, and it turned out it was 4.5 orbits. So basically, wherever you are in this process of trying to predict where the satellite re-enters, they were making quite large errors. So part of this was due to the fact that they thought that maybe the satellite would start to tumble at some point when the drag was too high, but actually the satellite is a sort of aerodynamically stable shape. It has these winglets at the back. It also had was completely functioning, so there were strong magnetic torquers that kept the satellite stable, and it basically flew like an arrow into the atmosphere. And they could even measure the temperature increase due to the drag when the satellite came at 150 kilometers. They could see the temperature of the batteries that are at the front of the satellite increasing more than the temperature of the instruments at the back of the satellite. So this was a very interesting re-entry experiment. Yes?
At what altitude does the drag make a transition from ballistic to gas dynamic? And is that taken into account when they try to model the re-entry?
Yes, that is taken into account. So there's a parameter for that in aerodynamics. It's the Knudsen parameter. That's basically the ratio of, I have to say it correctly, the mean free path length of the molecules in the atmosphere to the characteristic length of the vehicle. GOCE is not that large. It's a couple of meters. So for the space shuttle, you would reach this point at maybe 160 kilometers. We think for GOCE, it would reach that point. There's of course a sort of transition between rarefied flow and continuum flow. But for GOCE, we estimated it would reach this point at 140 kilometers. And as I will show here, this is an overview of basically the altitude during the decay. I show here also the solar activity, which showed some variation. It was magnetically quiet at the start, but there were some geomagnetic hiccups towards the end and here in the middle. I have a more detailed view of the last few days. So basically, the accelerometer started saturating a few days before the actual re-entry here. But it still was sending back data, but when the accelerations were too strong, it was basically flat. I will show it in a minute. And then there were a couple of passes over ground stations, and the last pass for which a data dump was performed of all the recorded data, so that we have a continuous time series, which we need for the accelerometer, was 5:15, and the actual re-entry was 5:15 midnight UTC. So it's basically a quarter of a day before the actual re-entry. That's when we have the last continuous data. Then they made a couple of short passes over ground stations where they just sent back attitude and GPS state data, so we could use that for the orbit determination, and we could use that to check that it was still flying like an arrow. And then at some point they said it's now going to splash in the Pacific Ocean, so we're not going to track it anymore. But it turned out that it made another pass over Antarctica, and it splashed into the Atlantic Ocean. I think it was the Indian Ocean and the Atlantic Ocean. So even then, this last orbit, they made the wrong prediction. That is a pity, because it would have been nice to get the temperature readings when it was really at 100 kilometers, if it was still possible.
What degree does it disintegrate before hitting surface?
So the space agencies, they have to, the space agencies that are well behaving, that includes NASA and ESA, they have to prove that the risk of a casualty is less than 1 in 10,000 for each re-entry. So they do actually a quite extensive analysis. They make a full 3D model of the satellite and all the materials, and they put it into a simulator where you can basically see the materials melting away and breaking up. And then for GOCE, I think it was a 1,000 kilogram satellite, more or less. They calculated that maybe 50 to 100 kilograms would end up on the surface. So that's a small fraction, but still enough to pose some risk. Luckily, it ended up in the ocean. Of course, there's a big chance that it ends up in ocean or in inhabited areas, and that's why it's, if you don't have a too big satellite with too strange materials, it's possible to reach this goal. This is what I already explained, basically, that the accelerometer started to saturate, but fortunately we could also estimate the accelerations from the GPS, and this actually gets better when the signal gets stronger. We have one measurement deteriorating and basically dropping out on us, but the other measurement getting better and better towards the end.
What do you mean exactly by saturating?
So this is a very sensitive instrument that was designed to make measurements at 250 kilometers altitude. So they have a certain range of where they can make these very accurate measurements. At some point, the accelerations become so large that basically I think physically what happens is that this proof mass, it hits the sides of the cage, and it cannot be electrostatically controlled anymore. So it reaches the maximum voltage that can be applied. And then you basically get this flat output beyond that, I think about 80 or 90 micrometers per second squared. I have so many nice results to show, so I shall hurry up a little bit. This is an animation that I made for the Space Debris Office that shows basically the difference between empirical models. So this is NOL MSIS, Jacquia Baumann, DTM, that's the French model. These are 3 different empirical density models. And we also included WACM-X, the previous version, in our study, and Ingrid Knosse made those runs for us. And you can see that there's quite already a difference in what these models look like in terms of their diurnal variability. And if I go back and forth in this movie, if I can, let's see, yeah, you can also see that there's this diurnal bulge at high altitude, and it turns into a bit more messy situation where you have multiple peaks and valleys at low altitudes. And NORMSys shows that quite nicely. And WACM-X, of course, tries to simulate reality, so it shows the most detail. But you can see that DTM and JB 2008 were not really designed for that. They keep showing only a few peaks. But still, all of these models, they keep up quite nicely with the general level of density. And this is a zoomed-in view. So the black and gray dots here are the data. The black ones are from the accelerometer. They show the most accurate data at the start, but at some point you can see them saturating and becoming inaccurate. And the gray one is from the GPS. And then all of these colors are the various different models. And you can see that there are some models that clearly stand out as not so good, but most models are more or less in line. And of course, not so good, you want to know how good or bad, so you have to attach some other graphs and numbers to that. So what we usually do is to compute the observed over model density ratio, because the density, it changes by a couple of orders of magnitude when you go over in these different altitude ranges. So you have to basically divide it by, for example, the model value to get the ratio. If you do the difference, then you get plots where you then cannot see any detail. And basically what you can see here is that there is this basically hiccup in how the model performs here on the 30th. That's when the geomagnetic activity started to kick in. And after that, it also becomes quite a bit more ill-behaved. So here, basically what you want is basically a constant line that it is not exactly at 1. That is to be expected because we have might have an error in the geometry of the satellite, and all of these models are based on databases of satellite drag, which might have had errors in the geometry, and we have had long-term change that's not incorporated in these empirical models like NORMSys yet. So that it is 0.7 instead of 1.0. That's not a big problem, but we do want basically this to stay on the same line. And so the light color is basically the 10-second data along the orbit, and the darker colors is the orbit averages. HASDM is the US Air Force empirical model where they basically assimilate their observations of the space surveillance network. So they look at all the space debris coming down, and they assimilate all of these decay rates, turn them into densities, and then update their model, I think, on a 3-hourly basis at least. And you can see that HASDM is much more straight. But as the satellite gets to lower and lower altitudes, HASDM starts to lose accuracy. TIGCM was also run by Ingrid Knosse. It does better actually during this period than NORMSys. So that was very interesting for me to see. WACM-X version 1 was basically the main model that we proposed to ESA to investigate. We wanted to turn on and off several options in the model to see whether we were missing any physics when we compared to NORMSys, for example. But you can see that the overall model behavior is a bit worse and was not really comparable to NORMSys. But still, it was interesting to look at it. If you look here, you can see a very interesting twice per day variation. So that means that there's an error in the model that varies twice per day. So I recently, with some help from colleagues here, ran the updated version of WACM-X, and you can see that it's actually quite a nice improvement. It's not perfect yet, but it's about at the same level now as TIGCM. And you can plot this also in terms of probability density. So this is sort of a histogram, and you can see that all of the models they underpredict. They overpredicted. Now let me see. Observed. The observations were lower than the model. GITM2 is the only outlier here. But Aaron Ridley basically tuned GITM2 using the data I gave him to end up here at 1. Now that's of course a strategy that might be valid. I don't know. The only problem is that since then we made a more detailed geometry model of GOCE, and we're basically scaling now. We can basically scale the GOCE data to this better geometry, and then basically GIDM is on the right of 1, and all these models they turn up a little bit closer to 1, but still the models are below 1 in general. You can also compare now the different models. There are lots of colors here. But you can see that WACM-X2 and TI-GCM, the models that were developed here, they are the best performance. They show the highest peaks here. So I was very pleased to see that. This other blue line here, that is the older WACM-X. So you can see that there's really a huge improvement in the WACM-X performance. Then it's also nice to look at some details. So here I like to make these types of plots where on the y-axis I have the argument of latitude. That's a term from astrodynamics. I teach astrodynamics at the university. But argument of latitude is basically very simple to understand. It is the angle along the orbit from the ascending equator crossing. So here you see all the orbits side by side. At 0, we're at the equator, going in the ascending direction, so from south to north. At 90, we're crossing over the north polar area. At 180, we're going from north to south. So for GOCE, this translates to dawn, and 0 translates to dusk. So here we're at dusk equator, north pole, dawn equator, south pole, and then we're back, and we can stack all these together. So I took a period where there was some interesting geomagnetic activity. Unfortunately, there were not that many big geomagnetic storms during the lifetime of GOCE. And the run I did for comparing all these models was for the year, the end of 2012 and the beginning of, and most of 2013. Yeah, there was not that much happening in terms of big geomagnetic storms. So this is the largest I could find. So AP is about slightly over 100, I think. And of course, you can now compare this to two models. So first, the empirical model, and you can see that it basically represents when the geomagnetic activity causes an increase in the density, but you do not see any detail. WACM-X looks like this, and if you compare WACM-X with the data, you can already see that there are features in the data that WACM-X represent, but still the data contains many more features. What I found interesting here is that it looks like WACM-X is showing the increase of the density maybe a few hours later than the data. So if I switch back and forth here, it looks a little bit like this peak shift. So that might be, so these kind of things might be interesting for modelers to look at how they set up the model response to several inputs that they're using. So if I look at HASDM versus the data, you can see that basically the peaks, they quite nicely align. With WACM-X, that is not really the case. So and these types of misalignments, they might also cause basically these wiggles in the time series plots that I showed earlier, and they might cause these kernel density estimates to become wider and the peak to become lower. So might be interesting to look at that. So I also want to talk a little bit about wind. As I showed in the beginning, basically we cannot measure the in-track wind, so we have basically a cross-track wind measurement. I always found this very hard to explain to people how to deal with this until somebody said, well, it's actually just like the Fabry-Perot interferometers that have a certain line of sight direction. So you can think of this as the GOCE satellite having a line of sight wind measurements. So it's in the data files, it's given as a vector in zonal and meridional components. But you should not misinterpret this as representing the full zonal and meridional wind. And if you want to compare with models, you have to be careful about that. So here I put a plot of the WACM-X wind field at some altitude. It's representative. And if you then evaluate the model along the GOCE track, you get, of course, the zonal and meridional components. And you cannot really compare these yet. So you have to basically take the projection of these vectors from the model with the equivalent vectors in the data. So you do basically the dot product, and then you multiply by the unit vector of the GOCE data. It's a simple operation, and what you end up with is this comparison. So now all the vectors show only the wind component in the direction that GOCE can measure. So for CHAMP, I also derived some winds that did not always work as well, but there are some situations where it seems to work better than others. Here you can again see the differences in the orbital planes. So this was in geographic coordinates. If you do it in geomagnetic coordinates, basically you put the geomagnetic pole at the center, and then you can see the orbit shift with respect to the geomagnetic pole, and you get suddenly a much better coverage for free. But also here you should be careful, because if we go back to the geographic coordinates, you can basically see, for example, for GOCE, that the satellite is always passing on the northern hemisphere on the day side, and always in the southern hemisphere on the night side. And if you look at the geomagnetic coordinate, you can see that there's a whole range in geomagnetic day side and night side with respect to the geomagnetic pole. But if you would interpret this in terms of differences between the hemispheres, then you're making a systematic error. So here I rotated it so that the noon and midnight is on the horizontal axis, and I show a movie that I made quite a while ago, where the CHAMP and GOCE measurements, they match quite nicely. So they're out of phase by half an orbit due to chance in this occasion. But you can see that they measure similar variations, even though there are some hundreds of kilometers distance between the tracks. It's also interesting to make comparisons with other measurements. This is also not so easy. This is a movie that illustrates how to compare with scanning Doppler imagers that are run by Mark Condy in Alaska. So there are 3 instruments here. And you can see basically that this instrument only operates at night. And GOCE, of course, goes from dawn to dusk. So there's only one pass at dusk, and then one pass at dawn, and that's what you have to deal with. And this is for the middle of winter. So in spring and autumn, you might not have any pass, and in summer, of course, it's out of the question at these high latitudes. So this is very difficult. So these are monostatic measurements from these scanning Doppler imagers. So that means that there's some assumptions going in, and you can see that there's also disagreement between the various instruments. Mark Condy, of course, has some techniques to if you combine the 3 instruments together, to get rid of some of these inconsistencies, to eliminate some of the assumptions that have to be made. It turned out that basically from this analysis, we saw that the GOCE winds were in general about 1.6 times as strong as the winds that were measured from the ground. But of course, this is a very limited geometry for the comparison. So it might also be interesting to look at comparisons with models. And we can basically bin the data. So here I took bins for high magnetic latitudes and very low magnetic latitudes, and both are for quiet conditions. And I did not really go into this. I explained it a little bit at the CEDAR talk. There are different ways that we can process the data. So we have, of course, now different versions of the model. We have RECOM X1 and RECOM X2, and RECOM X2 is much better. We also might have a GOCE data version 1.5, that's the current version, and we are currently working on GOCE data version 2, which might be a lot better. And one of the things that we're investigating is this aerodynamic model parameter alpha, which is an energy accommodation coefficient. It basically relates to how the particles that are bumping off the wall of the satellite, how much so they have a temperature when they're coming in, and they have a temperature when they're coming out. Do they keep their ambient temperature, or do they take on the temperature of the satellite wall? That's what this coefficient actually means. And the conventional wisdom in satellite aerodynamics is that 0.93 is a good value. So that's what everybody has always used, including me. I've experimented a little bit with it for some data sets in the past, but I never had good proof that it should be any other value. But actually, depending on the location where you're looking, this value can have quite strong effect on the distribution of the wind data that you're getting. And for example, in the North Polar Cap, it has a much stronger effect than in the South Polar Cap. You can see that in both cases, basically the peak gets higher. So that means that we're eliminating some of the tail, which might be an indication that actually these lower values are better values, that we're not mixing up something that is wrong in our aerodynamic model with the actual winds. But if you then compare it with the models, HWM 14 is the empirical model. It says that the distribution of the winds in the North Polar Cap is like this. TIE-GCM says it's like this. It's a general circulation model, so it takes into account a bit more weather type effects. This is a Potsdam general circulation model. This is the GITM model, and GITM actually gave very nice agreement with the wind. You could see that the densities might not have been so good, but Aaron Ridley was very happy to see this plot. And then if you overlay them all, you can see that there's quite, some disagreement about what the actual wind should be in the North Polar Gap, and there's more agreement in the South Polar Gap. And you can do the same exercise for dusk and dawn. Also for dusk, changing this aerodynamic model parameter changes the winds more than it does at dawn. At least it changes the peak value, the location of the peak. And then if you add all of these models, unfortunately I did not have the time to add GITM to this analysis. I could probably do that tomorrow. But you can also see that there's much more disagreement at dusk when compared to dawn. So we're now also analyzing the winds for this re-entry period. I showed that at CEDAR. I do not have the time to go into it here. I just want, yes?
Do you have a general idea why it is there is this discrepancy between the North Polar Cap and the South Polar Cap?
Yeah, that is a tricky question for me. I'm not a physicist. I'm an aerospace engineer, but I'm trying to learn as much as I can. So I have not really looked into this. Of course, you can do simulations with the model and try to sample the model in different ways. It might have to do that on one hemisphere, the satellite is always on the day side, and on the other hemisphere, it's more often in the shadow. And so that you get effects due to the ionization rate differing in the two hemispheres.
Control for seasonal effects? Or seasonal?
Yeah, so I took an entire year of data for this analysis. So this includes all seasons, but you can indeed make separate graphs for the different seasons here. There's a lot that we can still do with this data, and there's a lot that we can still learn from it. I think that might be an easy way out for me, but it might be interesting for me to work with other people on this. Hanli?
Well, I was wondering, can we consider the HWM result in just the effects from solar and geomagnetic?
Yes.
The others may have.
Yes, so HWM 14, I think, does not even include the F10.7 parameterization anymore. So it's only geomagnetic. Yeah. So I have a few more plots based only on the data that also go into this a little bit. You have to take into account what I said earlier about the sampling, but you can also bin all of the data geographically, and then you can also bin it by geomagnetic activity level. And here you can see, for example, that you have peak winds in the polar cap, both north and south, and then you have these return flows. But the return flows do not occur in the same magnitude in all longitudes. So, and the satellite does, of course, measure all longitudes equally because the Earth just rotates beneath the orbital track. So that's already interesting. That this might also have to do with the, so this is in geomagnetic coordinates, but it might have to do that the geomagnetic field is stronger at one pole compared to the other. It's more close to the dipole. So you can basically then turn the knob of the KP and see basically this return flow enhance and also go to lower latitudes. You can do it in local time coordinates. The same trick. And you can also look at IMF dependence. So this is also interesting because at first, if you do not know anything about the physics of the upper atmosphere, why would the flow of the neutrals respond to the measurements of the interplanetary magnetic field? But you can see that there's quite a strong pattern going on, and also a sort of symmetry. If you turn the interplanetary magnetic field Y component negative, you can see that there are the strongest winds are in the southern hemisphere on the dawn side. And if we turn it positive, then you can see it's in the northern hemisphere on the dawn side. Now, so the other work in progress, I think I'm running a little bit out of time. I went through this at CEDAR. If you're interested in what else I'm planning to do, well, there will be an update of all of this data. And I'm also looking into acquiring funding for processing future missions, GOCE follow-on and microscope, which is a current mission, but might have an extension for thermosphere measurements. And of course, we want to improve access to users and go to lower latency for space weather, model data assimilation, and open up new investigations. And I think it will be very interesting also to collaborate with people working on ICON and GOLD and work on this a little bit myself to compare the data from different missions and different measurement principles. So I started my talk with saying that this concept of the accelerometers and using them for thermosphere measurements can be made a little bit broader, because there are other instruments that make space weather measurements as well, even though they are not designed for that purpose. So I have a student now looking at the torques on GOCE and trying to get thermosphere data independently from the forces and from the torques. And to model the torques, he also had to look at the magnetic torques. And GOCE also has magnetometers for its attitude control. And he looked at the magnetometer data. And we're now involved in a study for ESA to see how these attitude control magnetometers can be cleaned up and try to get space weather data out of this. So this is, of course, sort of inspired by the Ampere project, which is very successful, and mainly because there are so many of these satellites. But for GOCE, it might also be interesting because of the very low altitude. We're very close to, we're basically in the F layer of the ionosphere. And you can see that there are clearly here at the poles, this is a similar type of plot as I showed earlier for the densities, very strong magnetic perturbations. This is the magnetometer reading that was calibrated minus the IGRF. You can see here at the end, something's happening. We looked it up. This was a redundant GPS receiver. Basically, during this period, there were 2 GPS receivers switched on, and one of them was switched off at this point. And so if you know about when such events happen, you can try to estimate the magnetic field influence at the magnetometer of the onboard equipment and try to correct for it. Another very exciting mission that has unfortunately come to an end last week is LISA Pathfinder. And LISA Pathfinder also contains magnetometers. LISA Pathfinder was a mission to demonstrate technology for measuring gravitational waves. So not gravity waves, gravitational waves. In Dutch, there are no 2 distinct words for this, so it's always very complicated. But so this is also a sort of fundamental physics technology demonstrator mission. There are basically 2 accelerometers with proof masses, and they want to see when a gravitational wave, basically, as I understand it, a sort of curvature of space-time passes through the satellite. Then these 2 proof masses, they will move with respect to each other. And for this mission, it was not possible to detect any, but they are going to, this was a study basically to put multiple spacecraft connected with lasers and very large distances. In any case, what they needed to know was what other forces affect the relative movement of these proof masses, and magnetic force could be one of them. So they put 4 magnetometers on board, and they tried to make the spacecraft very clean magnetically. And they put it into an orbit around the Sun-Earth Lagrange point 1. So that's basically the same place where the ACE mission is making its IMF measurements. And you can see the ACE orbit is here in blue, and the LISA Pathfinder is in red. So it's in a much wider orbit around this point, which means that there's quite some distance between ACE and LISA Pathfinder. So it's interesting to compare the measurements. Here you can see ACE orbit over its entire mission duration until January of this year. And then LISA Pathfinder we only have a couple of months of data. And in the end, we will only have a year and a half. Sorry?
What happened to that?
So the mission was over. They demonstrated that everything was technically perfect for the fundamental physics part. So now they have basically maneuvered the satellite out of this orbit because they don't want to have the chance that it might collide with another satellite in the future. And they're passivating the satellite. They will have no more funding to keep it operational. It's a pity that they did not wait on the outcome of our study and that they were not interested. I think they knew that we were doing the study, of course, but apparently there was no funding to keep it as a space weather monitoring satellite. But we have at least a year and a half of data of basically multi-point measurements close to L1. And the interesting thing is that halfway through the Least Pathfinder mission, also the Discover mission, of course, was made operational. So there are actually 3 points close to L1. So people who are interested in modeling magnetohydrodynamics on these small scales, they might be interested in that. I will quickly go through the slides. Basically, the data is very noisy, but if you take 4-minute averages, you can get a very nice signal out of it that compares very well to the ACE data. And you can see that there's some time shift here. And this time shift, if we use the solar wind speed from ACE SWAPAM instrument, and we apply a simple correction for this time shift based on the solar wind speed, we get actually a very high correlation of at least two of the components of the interplanetary magnetic field measurement. So I'm also not an expert on this, but if there are people interested in the data, I can make it available. It's on an FTP site. If you send me an email, I can send you the login information. And the project concerning the low Earth orbit engineering magnetometers is ongoing, and we expect to finalize this early next year. So maybe a presentation at AGU or EGU will follow about that. I don't have many results at this point. So I want to thank you for your attention. And perhaps answer any questions.
Yeah, so you showed that several models, the data to model the ratio is like about 0.7. So that would be a systematic difference between model and data. So is that because GOCE data is too low or the model too high or both?
So let me see if I can find that slide. I think it's both. So I already mentioned that we are making a new geometry model of the satellite that is much more fine in detail, and we use a numerical approach to calculate the aerodynamic force coefficients. And I think the multiplication factor, so basically that is a sort of refinement, but the major effect is that you get a multiplication factor. Of course, if we use the new model, everything will be a little bit refined with respect to just multiplying everything. The multiplication factor was, I think, 0.83 or 0.84, so that's already 15 to 20% that would be explained. And then still there will be about a 10% difference for this particular period. So this is a very short period of this orbit decay phase. If I would show the plot, I have made a plot for the older model, but I have not included WACAM-X2 yet. For an entire year, everything shifts a little bit closer to 1. So especially for this period, the models were over-predicting the density, I think, if I'm correct. Yeah.
Oh, okay, so this is, yeah, I know this is only like October 22nd to
Yes.
for this period.
Yeah, if you take another 3-week period, it might well be on the other side. And then if you take a year or you take multiple years, then of course this peak becomes lower and everything becomes broader, but it becomes more closely centered on 1. Yeah. But it might still not be exactly 1. There might still be a bias. Actually, we do not really know the absolute scale of the density in the thermosphere. It's a fundamental problem that basically all the good observations from satellite drag, they have this problem that the geometry model of the satellites that were used and the aerodynamic force model contains these uncertainties.
What's the longest period you actually compare the model with the GOCE data?
So for the empirical models, it's actually quite simple. I can just do it for the entire data set for all the CHAMP and GRACE and GOCE. I did it over starting in 2001 for CHAMP and ending for SWARM now. So that's 1.5 solar cycle. For the general circulation models, it takes a lot of computational time and disk space and to do this evaluation. Yeah. So I have only done it for 1 year for all of these models.
You mentioned at the beginning commercial satellite operators are interested in this capability. What is their current capability in this regime, and how do they go about calculating drag and corrections to their orbits?
Yeah, so it's the space operators at the space agencies. They basically use the empirical models, NRL-MSIS, I think mostly in the US and also in Europe, and the French, of course, they like to use their own DTM model, which is currently a little bit better actually than NRL-MSIS. And if their mission is in orbit for a while, they usually have some tracking data, and then they calculate from the tracking data a drag coefficient for their satellite. So, but if you would take these 3 weeks of data, for example, to calculate the drag coefficient for GOCE, and you would apply it to another 3 weeks, then in this other period, this drag coefficient, it contains, of course, it adapts for the model error during this period, and there might be a very different error in the NRL-MSIS model for this other period, and then they make mistakes like that. And so currently, for the most critical applications, such as trying to predict whether collisions will happen with space debris and active satellites, and whether you should maneuver your satellite away, they basically use very large safety margins. If the probability is, I don't know the exact number, but it's a very low probability, and then they already maneuver their spacecraft out of the way if they can.
And how about the low Earth orbit constellation operators, future principles OneWeb? You know, they're going to be low, so they're going to have to do this very actively. You know, they're looking into more exact methods, or they're just going to go in search of
I think, so I have not spoken to them, so I don't know about this, but I have not heard about them using or going to use more advanced methods. But of course, if there are large constellations that give uniform data and all these objects, all these satellites will have more or less the same shape and the same attitude control, it will be interesting for the community, and that means me, to make use of the data and try to get, especially if we can do it in real time, a sort of Ampere project going for satellite drag. Basically, the US Air Force is already doing that with their HESTM model, but I think there's no openly available alternative yet. So we have actually made a proposal to the European Union. Unfortunately, this week I found out that it was not granted. So we have to look for other sources of funding for that.
Satellite that is a perfect sphere
Mm-hmm.
and has an accelerometer inside, and just follow that thing.
Yeah, but it's always more complicated because even for a sphere, we do not know the characteristics of this gas-surface interaction completely. Ideally, we would also want to have a mass spectrometer that can be independently calibrated. We would need a GPS, but then you need to put an antenna, and it's problematic on a sphere.
Well, you would just make one measurement.
Mm-hmm.
You wouldn't have a complete set, but all of your unknown orientation would not be there.
Well, we actually know quite well the orientation of our satellites because they carry star cameras. So the orientation is not something I worry about. We have been maybe a bit lazy with modeling the geometry, but we're now putting in the right effort into that. We've basically used the geometry models that the manufacturers gave us, but we found out that these were not good enough. But the attitude is not really the problem. Of course, a sphere, it also is less sensitive to, for example, temperature variations. If there are so these satellites, they do not have sensors that measure the temperature of the gas, and the temperature of the gas also has an influence on the aerodynamic model parameters. And the more elongated the satellite shape, the more sensitive these aerodynamic model parameters are, because of the random thermal motion they bounce on the surfaces that are parallel to the flow. And for a sphere, you would have reduced that problem. Yeah. So, but there are many spherical satellites, not with accelerometers, but with very precise tracking as well, that are also used for aeronomy.
Then I have another question. I'm of course still curious about this difference in the modeling of the North Pole and South Pole behavior. So, for a moment, I assume, could it be that all of these models carry information on sort of the lower atmosphere in some way? Then, of course, there are, and the people in this audience who understand these things, but then there are in principle two obvious differences. One is that the southern hemisphere is a lot more ocean, and the polar area is one gigantic block of ice, and so that's the geometry, if you want. Another one is that whatever measurements go into the models that then model further up, probably the quality of the measurements, the density of the measurements that are being done on the northern cap is a lot better
Yeah.
than in the southern. So
At least for the lower atmosphere, that's, I think,
yeah,
true. Yeah.
and then sort of whatever
Yeah.
conjecture you make in modeling further up. So is it that? What?
Yeah, so I was actually part of an EC team on interhemispheric asymmetries with Aaron Whitley and Ingrid Knosse and some other people. And basically we concluded that we cannot answer this question from my data. So that was a bit of a disappointment because of this sampling issue. But there are other, so there's also the asymmetry in the magnetic field between the northern and the southern hemisphere. There is a slight eccentricity of the Earth's orbit, which causes the seasons to be slightly different in the northern and the southern hemisphere. So we listed all of these things that could influence things. But with the GOCE data, we look mainly at the GOCE wind data at the asymmetries, but in the end, you're making observation bias because on one hemisphere, the satellite is much more often in sunlight than on the other. So that did not come to a publication yet. So we should frame it in some other way than interhemispheric differences.
And the orientation of the solar magnetic field, the principal orientation, which phase of the solar cycle you are in, does that play a role?
So we have not looked at that for GOCE because we only have the upwards phase of the previous solar cycle for the GOCE data. So if we are going to reprocess the CHAMP data with a much higher accuracy and try to get also more wind data from CHAMP, so the CHAMP orbit precesses. So that means that if you take a long enough time span, you can eliminate some of these observational bias issues. But I think we are still limited in if you make a plot of basically solar activity, local solar time, day of year, and where all your measurements are, then I think you need several solar cycles to fill that complete space adequately.
Yeah, at least one full. That's the.
Yeah, I think one full solar cycle is not enough. Yeah.
I mean, 22 years.
Yeah, that might be.
Following up on that.
Yeah.
There's a poster at the Naval Research Lab with the comparison between the ground-based winds and the low winds and the mountains and steering wind factors with like fundamental operations. Are you compare with that kind of coefficient in there or what's
So let's see. That is something that I talked about at CEDAR. So we have these differences when we go to these different values of the aerodynamic model parameters. This is just one parameter, but we are working on including more parameters in our model that we can vary. With these very detailed geometry models, I have 2 students that are working together on that. One preliminary analysis that I did is I just took the two values, for example, the 1.0 and the 0.8, and I took the difference in the wind processed with one and the processed with the other, and the curve that came out showed quite some similarity with the curve made by Mambara Dudley of the wind. So that's a very good indication that these aerodynamic model parameter errors are responsible for the discrepancies between the ground-based winds and the satellite winds. But I think one parameter will not be enough to completely fix this. The question also is whether these parameters are dependent on the angle and on the temperature, and you can go completely crazy in parameterizing an aerodynamic model, but we do not have sufficient observations to estimate all the possibilities. But my students are going to try to do the best they can to come to a better version of the data next year.
GOCE has sampling issues, so what would be your ideal mission profile for getting all the data you want?
Yeah, so ideally you would want multiple missions. So GOCE has these sampling issues because of its sun-synchronous orbit, but the sun-synchronous orbit also brings many benefits because we can have solar cycle variations, and we do not have to worry about the local time, and we can look at day-of-year variations. We do not have to worry about the local time. So ideally, you could have, I would want a bunch of satellites, 6 orbital planes, something like Iridium, Ampere, and either have them all drift together or have them all in different sun-synchronous orientations. But yeah, I think one satellite in one orbital plane is never enough to resolve what we want to resolve. Yeah. But there is still enough that we can do in terms of comparing models with the data, even independently of whether we sample all parts of the atmosphere along all of the variables that are important.
The accuracy of the GPS in those satellites the same as the GPS is on the surface?
It's actually better because there is less ionosphere between the GPS satellites and the satellites and the LEO satellites. And we can use very advanced processing techniques. We of course know a little bit about the orbital mechanics, and so we can, for satellites that are above the atmosphere, 800 kilometers, for example, we have half a centimeter precision of the orbits. So if you go lower, it goes up to a few centimeters. For GOCE, we had 2-3 centimeter precision. So I think that's very, very accurate.
Yeah.
More than you would expect from experience with ground receivers.
I'm still wondering.